So, welcome everyone to the lecture series on electromagnetic waves. Okay. So, in last class we were studying about the force on the current carrying conductor due to a magnetic field. Okay. So, in the last class we have completed example number 4. So, in this class we'll try to touch upon example number 5, 6, and 7. Okay, and that will be the end of the part A of that module 4, and thereafter we'll start with the part B. Okay, so the example number 5 is find the vector force per unit length. We are supposed to find vector force per unit length okay, on two long straight parallel conductor if each carries a current of 10 ampere. Okay. To have two parallel conductors, they are long parallel conductors carrying a current of 10 ampere in the same direction. Okay. And the separation between them is, and they have given the d is equal to 0.2 meter. Okay. So I have taken the conductor along the, I'll try to show the figure something like this. Okay. And this is my axis. Okay. X, Y, and Z. Okay. So I have considered my conductor which is going into the mold, okay, and it is actually parallel to the y-axis. If you try to refer to this axis, it's actually parallel to the y-axis. Okay. This cross mark indicates that the conductor is going into the board. So it is something like this. It's going into the board, and here also it is going into the board. Okay. So when I say it is going into the board, means the current is flowing like this. Okay, here also the current is flowing like this. Yeah, and the separation between them is D. Okay. So I have taken this arrangement like this. You can take the you can take something different arrangement also. There is nothing issue in that because they have not specified anything that that this particular conductor is placed parallel to which axis and all those things. Okay, you are really free to choose the arrangements. Okay. So you could see that this particular, similar kind of problem really we have solved. Okay, that is while deriving the force per unit length or the force of interaction between the parallel conductors. Okay, it's exactly the same situation. Okay, so what you can do is you can try to find magnetic field at this point due to this conductor. Okay, I just trying to explain the procedure what we have done. Okay, and the detail you can really find out. You can find in the notes. So what you can do is you can find magnetic field at this point. Okay, due to this particular conductor. Okay, and similarly, once you try to find what is the magnetic field, okay, due to this current at this point, you can find force on this. You can try to find the force on this. Similarly, you can find the magnetic field at this point due to this conductor, and then you can find force on this. Okay. Force on this. They have asked us to find a vector force. Okay. Force on this. And we know that, as we have already proved in the last class, that if if you have a parallel conductors and if they carry the same current direction, okay, they will be attracted. So you could see that the force of you will try to find that the nature of the force will be attractive in the nature. Okay. If they are opposite, they will be repulsive in the nature, as we had already tried to prove. Okay. Exactly the same procedure I have done in the notes. You can really go through that. It's very similar to what we have done in the derivation part. Okay. Yeah. So yeah, and also I would like to show that is okay. And what will be the direction of the magnetic field at this point due to this conductor? Okay. So you could see that I mean due to this conductor, you can find magnetic field at this point. The conductor, the current is flowing like this. It is along the positive y-axis. You try to take your finger, you try to take your thumb along the direction of the current, and you want to find magnetic field at this point. You could see that it will be, you want to find here, it will be in the minus AZ hat. Okay. And similarly, you could also try to find what is the direction of the magnetic field at this point due to this conductor. You can try to point your thumb along the direction of the current, and you want to find a field at this point. So it is like this. It will be upward like this, and you want to find a field at this point. It will be upward plus AZ hat, and there will be minus AZ. That is, first thing we have to find B field. Once you have a B field, we know that the force on the filament is given by IBL cross B. Okay, first find B and then use this cross product to find the force. Okay. Yeah. So with this thing, let me go with the example number 6. Okay. So let me try to solve this problem in detail. The question is, a current of strip 2 cm wide carries a current of 15 ampere, okay, in the AX hat direction as shown in the figure. Find the force on the strip per unit length, okay, if the uniform B field is, okay. So you have a sheet current, okay, placed in a uniform magnetic field. So I'll try to draw the figure which is given in the problem statement. And so it is, the width is 2 centimeter. The W is given to be a 2 centimeter, okay, which I am trying to write it in the meters, which is 0.0 meter. Okay. And what I have given is the current of a strip 2 centimeter wide carries a current of 15 ampere in the AZ hat direction. So you have current flowing like this in this one. Okay. So the currents are flowing in the sheet of the strip. Okay. And you could see that you have a magnetic field. Okay. This particular sheet of the strip, okay, is placed in the uniform magnetic field, and you could see the field is uniform and it is in the direction of A by hat. So I would like to show something like this. Okay. Okay. So now the question is, we need to find a force on. We need to find force on this sheet. Okay. Yeah. Yeah. So so far we have found a force on the filament conductor. Now they are asking us to find a force on a sheet. Okay, sheet. It's a conductor. Okay, of a sheet. Okay, carrying current R. Okay. So we know that what is an expression for the force. Okay, for a sheet current. Okay, and it is given by like integral of K cross B ds. Okay, as we have a force on the filament as IDL cross B, we have an expression for the force on the sheet current is K cross B ds. Okay. Yeah, that is fine. Okay. Now, what is K? Okay, and we know that what is K is okay. is the current density, surface current density, and we know that it is given by, okay, it's given by like di by dl an hat, okay, or I can say it is I by dl an hat, okay. I is what is the flow of a current. Current flowing is given to be as 50 ampere, okay, and dl is the width, okay, and you could check that the width is 0.02. Okay. It's not a vector, it is simply I, it's di by dl or I by dl, 0.02, and an hat is same as the direction of the current flow, so which will be ax hat because the current is flowing in the ax hat. Okay. So that is our K. Okay. And we know that the unit of K is ampere per meter. Ampere per meter. It's a current per unit width. 15 divided by the width is 2 centimeter, which is 0.02. Okay. So we got to know what is surface current density, and we should know An hat is nothing but the direction of the current direction. That is like Ax. So that is our K. Okay. And we know what is our B. B is given like 0.2 A by hat. So it's quite simple. We can do a dot product now. Sorry, cross product. So we will check that A cross B is equal to 15 by 0.02 Ax hat cross. Okay. Then we have 0.2 A by hat. Okay. So Ax hat cross A by hat is quite simple. We know that it is Az hat. So 15 by 0.02 into 0.2 Az hat. Okay. Okay. So I think this will simplify to 150 Az hat. Okay. Now what is that ds? Okay, it's really quite simple. You could see that the ds is dx dy because it is in the xy plane. The strip or sheet is kept in the xy plane. So you can really integrate, and we will consider this particular length of this strip is of L, the width W and length L. Okay. So now the total force will be the integration of that 150 Az hat, okay, and that is dx dy. Okay. 150 Az hat dx dy. Okay. And now we should know what is the limits of the integration. Okay. So you could see the limit of the integration. I could take it as minus L by 2 plus L by 2 and minus 0.01 to the 0.01. In the simple, it is like 150 Az hat into 0.02 into L. Okay. Yeah. So that is will be the force, and we need a force per unit length. So it is F by L, which is 150 into 0.02 Az hat. Okay. That's all about this problem is. Okay. So let me summarize. The question was, there was a sheet current, okay, which is a very small, like a strip, which was placed in an uniform magnetic field. The width of the strip was 2 cm and the length of the strip was like L. And we know the expression for the force. We know the force on the sheet current which is placed in the magnetic field is given by this. It's a K cross B ds. Okay. And the question was, what was the K for this? Okay, they have not given the K, but they have given the information that is current flowing in the, like 15 ampere current is flowing in the x direction, and the width of the strip was given like 0.02. And we know what is the definition of surface current density, which is given like di by dl A hat. Okay. So di by dl A hat, and A hat is A hat is same as the direction of the flow current. We know what is current, which was given 50. We know what is the width. Okay. The dl is the width, which was 0.02. So I by dl or I by L, whatever it is. Okay. And that is what we have got a K. So once you have a K, we did a cross product with that. And then to find a force, we need integration. But actually, we could see that as this is particularly integrand is constant. Okay, we don't require actually integration. Okay, simply you can multiply with an area. Okay, simply you can multiply with area, and that is what we got the things. Okay, as the strip is located half in, the strip is located half in the negative portion and half in the positive portion. I have taken the limits as minus 0.01 to 0.01. The width I have taken like half over that. Okay, and similarly the length I have taken half on the left hand side, half on the right hand side. Okay, so this is all about the force on the sheet current. Okay, fine. So next example number 7. So you have a conductor of length 2.5 meter located at z equal to 0, x equal to 4, carrying a current of 12 ampere in the minus eva hat direction. So now you have a conductor of a length of 2.5 meter, which is located at z equal to 0, it means in the xy plane, and it is at x equal to 4. So from here at x equal to 4, in the minus a1 hat direction, you have a conductor, okay, and its length is 2.5 meters. Okay. And it carries a current of 12 ampere. Okay. And it is placed in the uniform magnetic field, okay, B. If the force on the conductor is, it's given that the force on this particular conductor is F is equal to 1.2 into 10 raised to minus 2 Newton, okay, in the direction of, they have given the direction as minus ax hat plus az hat divided by the root 2. Okay. So this is the arrangement. The problem statement is you have a conductor of 2.5 meter length, okay, carrying a current of 12 ampere in the minus eva hat direction, and this particular conductor or filament is placed in the magnetic field B, which is unknown to us. Okay, here the B field is unknown. Okay, and they have given the force on this particular conductor as this much. And the question is, we need to find this particular B field. We need to find this B field. Okay, so it's quite simple. We know that the force on the filament, okay, and it is being mentioned that the B field is uniform. It is being mentioned that the B field is uniform. Okay. So we know that the force on the filament in a uniform magnetic field is given by F equal to, let's I L cross B. Okay, it's given to me as I L cross B. So well, we know what is on the left hand side. It is 1.2 into 10 raised to minus 2. Okay, into minus ax hat plus az hat divided by root 2, okay, and this should be equal to, that is 12, I is a 12 ampere. What is L? L is a vector, okay, and its length is 2.5, and the direction of this length is same as the direction of the current, which is in the minus gamma hat. So it is minus gamma hat, okay. So minus gamma hat cross B, So and we really don't know what is the B is. It's really unknown to us. So we'll take that B is equal to Bx Ax hat plus By A1 hat plus Bz Az hat. Okay. So we'll try to perform the cross product at the right hand side. Okay. And whatever we get the result, we'll try to equate the coefficient of left hand side and the right hand side to find these unknowns Bx, By and the Bz. Okay. So it's quite simple. So I'll try to do this right hand side, which is 12 into 2.5 minus A1 hat, and we are supposed to do a cross product with this B. Okay. As I told, the B is like so we have like Bx Ax hat plus By A1 hat plus Bz Az hat. Okay. So you can really check this cross product. Okay. So I write down this answer. Okay. So we get the cross product result as minus 30 Bz Ax hat. Okay. Plus 30 Bx Az hat. Okay. I try to do this cross product with the determinant, which I'm trying to show here. Okay. So I mean we can do it like this. Okay, we can do this individual like A by hat cross Ax hat and then with that one. Okay, but I try to why we have trying to do with the determinant. So it's a cross product between these two vectors. So we know it is Ax hat, Ay hat, and Az hat. Okay. And this vector is like 0, has only y component. So it has only y component, which is 12 into 2.5 minus Ay hat and 0. And then you have Bx, By, and the Bz. Okay. So when you do this determinant, you get this result. Okay. Yeah. So we have computed the right hand side. So now we can equate the coefficient of left hand side and the right hand side. That is, now I could say that 1.2 into 10 raised to minus 2, that's minus Ax hat divided by root 2 is equal to this Bz. That is equal to minus 30 Bz. And similarly, I could say 1.2 into 10 raised to minus 2 divided by root 2. Az hat is equal to 30 Bx. Okay. So with this, you will get what is Bz and Bx. So just we need to solve it. Okay. So when we got to know what is Bx and the Bz, the question remains what will be the By component. And you could see that something interesting when you really perform the determinant. Okay, the By, I mean there is no term By. Okay, there is no term By. Okay. So because when you try to perform the determinant, okay, Az hat times. Okay. So when you perform this, you could see that it is Bz into this term. Okay, minus 0 into By. Okay. And similarly, when you try to do one more thing, okay, which you could see it will be like 0 minus 0 minus a bar hat times 0 minus 0. And when you try to do this one, again you could see it will be 0 minus bx times this term. Okay. So, sorry, this is not the here, only we have to write the component one. Okay. It will be just, yeah, it will be minus 12 into 2.5. We need to write only component parts. Okay. Yeah. So you could see that the first thing I'm trying to say that the by component has not come into the picture. Okay. I'm getting the result of the determinant. Okay. So that, okay, you can really choose any value of the by. Okay. So I'll try to write here any value of by. Okay. We'll hold this result. Okay. I mean we'll get the same answer. Okay. You can take any value of the by, still the determinant remains the same, and hence we can write the b field as whatever we get bx while solving this, and whatever we get the b side, and here you can write it as anything. Okay, still the answer remains the same, that is force will remain the same. Okay, so this is all about the example number 7. And the example number 8, okay, is really quite simple. That is, two infinitely long straight conductors are located at x, y, 0 and x, y, x equal to 0, y equal to 10 meters. Both carry a current of 10 ampere in the positive AZ hat direction. Determine the magnitude of the force experienced. Okay. So you have two parallel conductors. One is placed here and one more is placed parallel to the z-axis. One is passing to the origin and one more is passing to y equal to 10 meters. And both of them carry the current 10 ampere in the same direction. Okay? And now they are asking to us to find only the magnitude of the force. That is, it is not a vector force. Okay? If it's a magnitude, we have a straightforward formula, that is force or force per unit length. Okay? They have asked force per meter. Okay, so this F by L is given by straightforward mu naught times I1 I2 divided by 2 pi d. Okay, it's a Newton per meter. So if you are really not interested in the direction, so you can use this straightforward formula which we have derived in the previous class, mu naught times I1 I2 and the 2 pi divided by 2 pi d, that is separation between them, which is 10 meters. Okay, that's quite simple. If you are really interested to find the direction of the force, then we can go the same procedure as I explained at the beginning of the class. So try to find magnetic field at this point due to this conductor and then find the force on this conductor. Similarly, find magnetic field at this point due to this conductor and then find the force on this. So you will get the force on each of the conductor. Or else, what you can do as smart thing is that you can try to find the force on one conductor. Okay? Try to find the force on one conductor. And we know that we really obey the Newton's third law. We could say that F2 will be equal to minus times of the F1. Even that is also will be correct. And you could really check that if they are really in the same direction, the region of the force will be attractive. Okay. So this is all about the problems, okay, on the part A of the module 4. Okay. So if I really try to summarize what we have done in the part A, okay, we started with finding the force on moving charge in the presence of both electric field, magnetic field, and the combination of both the fields. And then we found the force on the filament, sheet current, and the volume current, okay, which is placed in the magnetic field. Okay. Then we try to find the force between differential current element and the force between the conductors. Okay. And then we form the force between parallel conductors. Okay. And then we have worked on the some numericals. Okay. So now let us begin with part B. Okay. So part B. Okay. As I said that here we are interested to study the magnetic field. Okay. That is magnetostatic field in the matter. Okay. Before that, we need to study the concept called magnetic torque and moment. Magnetic torque and moment. Magnetic moment. Okay. So we know that so far we have studied the force on the conductor, which is placed in magnetic field. So now we are interested to study the torque. Okay, that is magnetic torque. Okay, on a conductor which is placed in the magnetic field. Okay, and this particular concept of finding magnetic torque, okay, which is placed in magnetic field, is very important. In understanding the behavior of DC motor. Okay, that is understanding the concepts of DC motor and the generators. Okay, they play a very important role. Okay, so before we try to study about magnetic torque, let us have a quick review about the torque what we studied in the physics. Okay, so we know that the torque is defined as torque is a vector quantity, okay, which is defined as R cross F, and we know what is R is. R is moment R. It's moment R, and F is the force we apply. Okay. Say for example, if I try to take some kind of nut bolt, and you have a span. Okay. So we know that this point is fixed. Okay. And with this spanner, we are trying to rotate this particular. With this spanner, we are trying to apply a force, and we are trying to rotate it. Okay. So we know that we apply force at some point, F, okay, and we define this particular moment R, okay, which is from this fixed point, okay, or you could say it as an origin, and to a point where we are going to apply the force, and we call it as an R. It is moment R. Okay. Yeah. And we know that the torque is given as it's a cross product of R and the F. Okay. As I said, it is a vector, okay, and we know that the direction of the torque will be a cross product of R and F. So you could see this is the R joining the fixed point to the point where we are applying the force. Okay. So you could see that when you try to perform a cross product, okay, and we know that we can find the direction of the cross product using right hand rule. Okay. So we can try to I can extend this. This is my R and this is my F. It's an R cross F. So you can try to take your palm, okay, along this R and try to turn towards the F, and the thumb will point in the direction of the torque. R is this. Try to rotate. Okay, first thing you have to try to align your palm to in the direction of the arm. Okay, and try to rotate your fingers towards this F. Your thumb will point in the direction of the torque. Okay, and the torque direction will be like this. And we also know that the direction of the torque will be in the direction of the axis of rotation. Okay, because when you try to take a spanner and try to rotate, okay, you could see that the rotation will be like this. Okay, and the axis of the rotation is this one. Okay, this is what we know from the physics. Okay, we know how the torque is defined. It's a moment arm with the force applied. Okay, and I try to explain what it is, what is R and what is F. Okay, yeah. So from this, what we come to know that whenever you are trying to define a torque, there are two things important. The one thing is the fixed point or a origin. Okay, or we could say that the point at which we are going to define a torque. Okay, that's a fixed point. Okay. And one more is the point at which we are applying the force. Okay. If we are really clear with these 2 points, okay, we can really define the torque. Okay. Say, for example, I would like to define something like this. Okay. Say I want to find the torque at this particular point origin. Okay. It is defined about the origin. And say that at this particular point I apply a force. Okay. This is my point P and I apply the force. And we know that we can define this moment arm, okay, which is joining from this particular point, okay, origin point, okay, or a fixed point about which the object is rotating as moment arm R, and this is my F. Okay. Yeah. So we know that the torque will be perpendicular to this boulder vector, okay, as I just now explained. Okay. So we could see that we can do again. I can just extend this R, okay, and you could see that R cross F will be perpendicular to this particular xy plane, so which I can try to show the torque will be in this direction. That is one torque. Yes. Okay. And as I said that torque can be defined in terms of the cross product R cross F, and we know that we can try to write this as R, that is magnitude of R times magnitude of F, and sine of angle between the R and the F, and A hat. A hat will be unit vector perpendicular to this both the vector containing the plane. Yeah. And the alpha is an angle between the F and the R. Okay, that's fine. Now, what is one more interesting point I want to study before I go into this magnetic torque? Okay, so right now we are doing the review of a torque. Okay, say for example, I have a situation something like this. I have 2 points, P1 and P2, okay, and I am defining my torque about the origin O. This is my fixed point, and I have my moment R. Here is R1 and here is R. Okay. So you have force on this as F1. And you have a force on this as F2, which is minus of the F1. Okay, both of the magnitude of this both the forces are the same, okay? And they are in the opposite direction. Let me define one vector from 2 to 1, which I am going to call it as R2 1. Okay, yeah. So now what I can say that, okay, so what interesting we can try to show that. Now the total torque, I can define it as, okay, that is R1 cross F1, okay, R1 cross F1 plus R2 cross F2. Okay. So you have two forces. Okay. So I have tried to calculate the individual contribution of the torque R1 cross F1 plus R2 cross F2. Okay. So what I said that F1 and F2 equal to minus F1. So I can try to plug in that. So it is R1 cross F1. So minus R2 cross F1. So you could try to check that. I can try to write it as, I'll try to take this minus sign. Okay. So the total torque is like, if I take common F1, so R1 minus R2 cross the F1. Okay. And you could check that this R1 minus R2 vector is nothing but this R21 vector. So which we could write it as cross F1. So what was a very important, the thing to derive this particular result was that is F2 was equal to F1. Or I could say that the total force on the system was 0. Okay? Because of F2 equal to minus F1, the total force on the system was 0. Okay. Now what is the interesting fact as I was telling you this? Okay. So you could see that the D1, which was dependent on the moment of R1, okay. But you could see that the total torque is R21, which is the distance vector between F2 and the F1. It is not dependent upon the R2 and the R1, that is moment R. Okay. Yeah. So the total torque is not dependent on this individual moment R. Okay. And what I can really therefore conclude that the torque is also independent of this origin where we define the torque. Okay. So this is what an important result. What I want to write is so I can say that torque is independent of choice of origin. Choice of origin. It is provided total force is 0. This is true provided the total force is 0. Okay? Yeah. So why we are trying to say that? Okay. So the R21, okay, which is the distance factor between these two point P2 and P1 is really independent of this R1 and R2. Okay. I can choose some other reference point. Okay. Other reference point. It is really independent of that one. Okay. Because it's all dependent upon this factor. So that I could also say that the torque is independent of the choice of the origin, provided the total force is 0. Okay. Yes. So with this review of torque, so now we can go for the magnetic torque. Okay. So from this review of torque, we have learned how the torque is defined. Okay. And to define torque, we need 2 points. One is the point of origin or the point where we are going to define a torque, and the one more point where the force is applied. And the torque is given by the cross product between moment R and the force of application. Okay. And we know how to find the direction of the torque. And also we said that, okay, one very important point about the torque will be always, okay, along the direction of the the direction of the rotation axis of rotation. Okay. That's an important. So with this, now let us try to find a torque, okay, on differential current loop. Okay. So let me consider a differential current loop. Okay, that is dx and dy. Okay. That is y. So I have taken the margin field B. Okay. So you have a loop which is placed in the xy plane. Okay. Yeah, you have a loop which is placed in the xy plane. Okay, in a magnetic field B. So I can divide this loop into the segments like 1, 2, 3, and 4. Okay, 4 segments. Okay. Yeah. So now, before I proceed, there is one interesting fact. Okay, we know that the force on the filament, okay, is given by like minus I integral of B cross dl. Okay, so if I say that B is uniform, B is uniform. Okay, when I say B is uniform, I can really pull it out from the integration. Then you would say that it's minus I times B. Okay, B cross. That is closed loop. It's an integration of a dl around the closed loop. Okay. And you could check that. Okay. The integration of this, okay, around the closed loop will be a 0. Okay. So it is quite straightforward. Okay. So it means that you are trying to add this vector lengths. Okay. Okay. If I try to find what is this sum of this vector lengths, you could see that for one segment it will be positive, whereas in the other segment it will be negative. Similarly, for one segment it will be positive, and the other segment it will be negative. Okay. So total sum of that will lead to 0. So which means that the force on the loop, okay, so this part is 0, so the force will be 0. So this is something interesting. Okay. The total force on the loop, okay, on the loop, which is placed in uniform. This must be the condition. The B field must be uniform. The force will be 0. Okay. So it doesn't really mean that the torque will be 0 because because that forces are acting at different points. Okay, the forces are actually acting at different points. So that as a total, the force will be 0, but there will be a torque. Okay. Yeah. So this is a note before we try to find the differential torque on this loop. Okay. Yeah. So now what I'm trying to say that, okay. So the first thing I say that the B is equal to B naught at the center of the loop. The center of the loop. Okay. And the next thing what I want to say is, okay, as this particular loop is a very small loop, it's a differential loop, okay. So what we can really assume is that, so whatever the value of the B field is at the center, it will be the same even at these particular segments, okay. As we are taking a very small loop, okay, the B field will be the same all along this loop, okay. So what does it mean? The B is uniform along segments. along segments, and its value will be B naught. Its value will be B naught. So just now, as I said that, okay, if you are placed a loop in a uniform magnetic field, we know that the total force on the loop will be 0. Okay. If the total force on the loop is 0, as I said just now, okay, the torque is really independent of the choice of the origin. Okay, so you are really free to choose the origin or the point at which you really need to define the torque. Okay. So now let us choose, okay, the origin, the point where we need to define the torque as at the origin. So we are free to do so that. Okay, you are free to do so provided the total force on the system should be 0. And as I said that with this condition, just now I said the total force is 0. Okay. So with this, we can really do this quickly. Okay. So what we'll do is we'll try to find the force on this particular segment. Okay. And then we'll try to find what is the contribution of a torque on this segment. Okay. Similarly, we will be doing on segment 2, 3, and 4, and there we will find the total differential torque. Okay, on this particular loop, which is placed in the uniform magnetic field. Okay, so let us do it quickly. So what is dF1? Okay. The dF1, the force, there is a force on the filament which is placed in a uniform magnetic field, is I dl1 cross B naught. Okay, I dl1 cross B naught. And what is dl1 naught is it's along the x-axis because this is my x-axis. So it is dx ax hat cross B naught. Okay. And we will take the B naught as B naught Ax hat, it is B naught X Ax hat, B naught Y Ay hat plus B naught Z Az hat. Okay. That is the general B field at the center. B naught X Ax hat plus B naught Y Ay hat plus B naught Z Az hat. So that is what we have B naught X hat plus B naught Y hat plus B naught Z Az hat. Okay. So you can really check that the cross product will lead to an I dx Ax, sorry, it will be I dx, okay, times B0Y Az hat minus B0Z A1 hat. So that will be the force on this particular segment. Okay. Now, what is the contribution of a torque on that side? So it is dt1, which is moment of r. Okay, moment of r1, dr1 cross df1. Okay. Now, as I said that we have taken the origin at the center, so the moment of r will be from this origin to this particular, I mean, you could say that the midpoint of that segment where the force is lie. I mean, where it is, we have a force. Okay. So you could see that I can really define this moment of r. It is going towards the negative x-axis. It is 1 by 2 dy. Because this is whole dy, it's exactly half. I can say that it is minus 1 by 2 dy a1 hat cross that df1. Okay. So you can really check this cross product. Okay. And I'll try to write down the final result. It is minus 1 by 2 dx dy I b naught y ax hat. That is the torque contribution from the side 1. Okay. Yeah. So what is something interesting? You can really check that dt3 will be same as the dt1. Okay, will be the same. Similarly, now you can find dt2 and you can really check that dt4 will be also the same. And what will be our total torque? Will be total torque, okay, is equal to dt1 plus dt2 plus dt3 plus dt4, okay, and the detailed things you can really find out in the notes. I'm writing the final result, okay. So dt will turn up to I dx dy a z and cos b naught is not, sorry, the actual result will be I dx dy, it will be b naught x ay hat minus b naught y a x hat. Okay. Now, this result which is within this bracket, I can write it as I dx dy, okay, as a cross product is at cross b naught. Okay. And now you will see that I can write it in much more better. This is I ds, I ds cross b or b naught, whatever it is. Yeah. So I have tried to show some results. Details you can really find out in the notes. So what is the nice result? We got the differential torque, okay, on this rectangular loop which is placed in a uniform magnetic field leads to a nice result I ds cross b in general. Okay. By deriving we have taken it as b naught, but now I can write in general I ds cross b. Okay. So we will stop this lecture over here. Okay. And in the next lecture we'll try to conclude. We'll try to start from this particular point. Okay. That's fine.